normally Shija does this, but my name is Adam, and I am the social media coordinator for Astronomy Club at York University. So today, we are so fortunate to have Rayhan talking about LIGO and gravitational waves as well as field equations. So thank you so much. And just a little bit about Rayhan. He's actually a high school student. So we are really good to have him.
Thank you so much. Thank you so much. Okay, cool. Let's click play and let's go for it. Well, today, as you might see, I'm here to present on the Laser Interferometer Gravitational Wave Observatory, more commonly known as LIGO, gravitational waves, and Einstein's field equations. Now, for the questions, if you do have any questions, if you do, please, it's completely informal. You don't really have to wait till the end. I do realize that there is a designated question time, but if you want, you can just raise your hand and sure, yeah.
What high school did you go to?
Oh, I go to Richmond Hill High School.
And how old are you?
I am 16 years old.
Okay.
I realized I should have mentioned that. So all the equations that you will be seeing have been written on my whiteboard at home because either I couldn't find the variables or the form of the equation that I wanted online. So do excuse the handwriting that you might see.
Why didn't you just type it up in Microsoft Word?
Because I'm not that advanced. So I'm going to assume, I am going to be assuming some things from a lot of you. And once again, so if you ask for the derivations, I will be providing them because I got them all on my sheets right here. But I am going to be assuming some subtextual definitions when we come to the field equations, such as a multivariable, or to make it sound cool, multi-dimensional calculus, some differential geometry, and a little bit, I'm just going to be introducing you to tensor analysis. So this should be a really good, fun ride. So before I actually start, let me just summarize the major topics. That didn't work. Let me summarize the major topics that I'm going to be talking about. So we're going to be starting off with some general facts on LIGO, what it is, how it works, and why it's even there, what's the purpose of LIGO. And then we're going to be getting into a little more theory on what LIGO is really doing and gravitational waves. And then we're going to come into the best part of the presentation, math. Because this is where I'm going to be summarizing everything and kind of putting into the field equation and showing you how the field equations can actually show us that gravitational waves exist. And then I'm going to end it off with the hypothetical graviton and how it can kind of sort of make sense in the field equations. But as you might know, a theory of quantum gravity hasn't been made yet, so it's not exactly in the field equations, but it sort of fits, and we can actually get or deduce many of the properties of a graviton from understanding the field equations. So let's get straight up to LIGO itself. We have two facilities in LIGO, one in Hanford, Washington, and the other in Livingston, Louisiana. Now there are two facilities for a simple reason, to actually make sure that the detection that is detected is actually a gravitational wave. Many times they can be sound waves, earthquakes too, maybe if it's on the fault line. But generally speaking, if one observatory detects a gravitational wave, usually it's about 7 milliseconds after the other one. And if they match up, which they did for the first one we measured in 2015, a gravitational wave can be inferred. So the signal is the same, that's the main property, and I'm actually going to be showing you what the signal was and what that signal actually means. So LIGO is actually thinking of more facilities around the world, such as LIGO India. So I'm actually very excited because I'm from there. So it's going to be a lot of fun to actually see what they actually implement. So a very big question with people in LIGO is, how does it really work? So LIGO works with the basic principle, as the name suggested, interferometry. Or technically the apparatus used in LIGO is the Fabry-Perot-Michelson's interferometer. And I'm going to be getting into the difference between that and a basic Michelson interferometer. But don't worry, if you don't know what interferometry is, that's what this is for. So this is a basic Michelson interferometer right here, where there is a laser basically being outputted. Now LIGO has a laser that outputs light at a wavelength of 1064 nanometers and an output capacity of up to 200 watts. So there's a polarizing beam splitter right here. Now, interferometry works with the basic principle that light is always unpolarized. So when it actually hits the beam splitter, it splits up into two types of polarization, P polarization and S polarization. Now P is actually kind of like a short form in German for parallel, and S loosely translates to perpendicular. And that's basically how one is going in one direction and S is going in the other. So those two are mirrors, or in LIGO terms, they actually call them test masses many of the times. So they hit the mirrors and they come back to the beam splitter, finally for recombination. Now, due to the superposition principle, the light can either have a total constructive interference or a total destructive interference, depending on the apparatus. Now, at LIGO, it has a total destructive interference. And I'm going to be coming into why that might be. So if there is some sort of phase shift between the light, there will be a light actually produced, and this is the most important part of the entire apparatus, the photodetector. So I'm going to be getting a little bit more into this and comparing how this actually matches up with actually LIGO's apparatus, because it's very important to actually understand the difference between a basic Michelson interferometer and a Fabry-Perot Michelson interferometer. So this right here is the Fabry-Perot Michelson interferometer. As you might notice, the only major different things is a power recycling mirror and these mirrors right over there. So this is actually a pretty neat apparatus, and it goes under a pretty nice understanding. So once again, as I mentioned, the laser output capacity of 200 watts, wavelength of 1064 nanometers. And now the power recycling mirror is there for a simple reason, so that when the light comes back to the beam splitter and back to here, the laser doesn't have to keep outputting the same energy, but it can just be repeated over and over again. Obviously, if there is a light ray detected, which every second of the day obviously isn't, if there's a light ray detected, then this will not even take place because it doesn't matter. But if it's completely empty, which is most of the course of the year actually, there will be this complete bouncing back simply to save energy. But here we have the two double test masses, and now we actually come to the definition where this is the Fabry-Perot cavity. So many people understand that LIGO's arms are 4 kilometers long, but they actually don't know that the arms aren't really 4 kilometers long. It's this cavity that's 4 kilometers long, and that's a very big difference because this also has some actual width, right? So because this one is a little bit longer than this width, actually if you can see over here, this is a little bit shorter than this. Because of that, the waves can actually have a total destructive interference. Otherwise, they will be having exactly the opposite phase shift and they will be constructing, but that's not actually happening. So because of this mirror right here, now the purpose for this is to basically bounce light back and forth 280 times before recombining at the beam splitter. Now the purpose for that is pretty simple because we know gravitational waves are very, very, very weak. Gravitational waves move Earth and space around us by 10 to the negative 18 meters. That is 1,000 times smaller than the width of a proton. So because it's so small, it's not really easy to detect, and you don't see space around you moving everywhere. Hence, there's this and this mirror over there, basically the bounce back light back and forth 280 times to theoretically lengthen the distance. Now the purpose for this is actually pretty simple. Once again, as I mentioned, as you might know, the intensity of gravity follows the inverse square law, and because, as we know, it's not really how gravitational waves are formed, but when gravitational waves are formed. We know that gravitational waves, usually the binary black hole collisions, are formed billions of light years away, therefore billions of years ago, and has to travel all of that distance. It might be in almost a perfect vacuum, but it's still traveling a very long distance. Hence, the intensity of gravity has shortened by a lot, and that is why this is there over here. So, this is pretty interesting to actually understand how LIGO works, and now hopefully you understood why it's there and what it's actually doing, measuring gravitational waves, and seeing if there's really anything. So now you might be asking yourself, well, what's the point of actually doing this? Gravitational waves, as you might know, are really the key to proving Einstein's field equations, which I will be getting into in a further slide. So understanding gravitational waves and why they're so important is really there to prove Einstein's field equation. And as we know, in September 24th in 2015, the first gravitational waves were detected by a stellar mass black hole collision. I'm going to be getting into different types of gravitational waves, so that might explain a lot. But generally speaking, this is the apparatus setup. So, photodetector, the most important part. The photodetector is an indium gallium arsenide photodiode with a very high quantum efficiency for detecting light at 1064 nanometers. Now this obviously, as I mentioned, is the most important part of the entire apparatus because this is what determines is there a gravitational wave or isn't there. So just understanding how this works. So after 280 times it's bounced back and forth, it comes back to the beam splitter over there. As I mentioned, the goal is a total destructive interference. However, when there are gravitational waves, it shifts space a little bit right, a little bit up, because it has a polarization, much like light, of H plus and H cross. So because of its polarization, it can actually stretch space back and forth, which will induce a phase shift. This phase shift, when actually recombining at the beam splitter, will then split back to the photodetector and actually produce a produce a light ray. I do have an animation for this if you understood nothing of what I said, because that was a bit choppy explanation of how it really works. I do have an animation, don't worry. But right now I'm just going to be showing you what gravitational waves are. So this is two stellar mass black holes, an animation of them. Hopefully you can basically see. And that right there is the peak amplitude you can see over there right when they combine. So when they combine, now the first gravitational wave ever detected released a total mass of 3 solar masses only in gravitational waves. Remember, 3 suns only in G waves. And all of that energy, the most of the energy lies here in the peak of the wave. And when we actually detect it at LIGO, we actually get a certain frequency. Because we have a certain frequency, we have a certain amplitude, and LIGO, what they've actually done is they've even converted it to sound so that we can hear. And when I get into different types of gravitational waves, I'll actually make you listen to what gravitational waves might sound like. So this is basically the apparatus here set up. This is a small animation that I got from the National Science Foundation. So that's the beam splitter. Splits it up into P and S polarization. Now the Fabry-Pérot cavities are not included in this for some reason because I guess simplistic purposes. But there are Fabry-Pérot which basically bounces light back and forth 280 times. So there, as you can see, it's a total destructive interference or 180 degrees out of phase. That's the purpose. However, when there are gravitational waves, it moves space either up or to the right, depending on its polarization, which then creates a light ray which can be detected by the photodetector. This is just going to show you a little more on what is actually happening here. So the moment you actually produce a ray, we're getting some level of phase shift over there. And the maximum level of phase shift, meaning when the crest is with the trough, when the crest is with another crest, meaning total constructive interference, that is when you will get the maximum peak amplitude. And as you saw over there, that maximum brightness, or the maximum amplitude when the two black holes actually converge, that was when the phase shift was at the maximum, or exactly sort of when the crest was with the crest. Okay, so any questions? Go for it.
How do they tell which arm is contributing to the distortion?
So what actually has to be seen on that is, okay, do I have a picture of it? Sorry. If I do have a picture of it, right here. So when we actually get to this, what we're getting into, the main purpose of the entire LIGO Observatory isn't to really see which arm is contributing. Even though that's a good question, it can't really, it can be told by its polarization. So the polarization, once again, depends on how the gravitational wave was emitted, what's actually happening when the gravitational wave was emitted. Is it a continuous gravitational wave? Is it a burst gravitational wave, which we're going to be coming into? What are the different types of gravitational waves? Now that will tell the energy output. The energy output will tell us the polarization. The polarization will then once again tell us how much does this stretch or how much does this stretch. So once again, the main purpose of LIGO isn't really to tell which one is contributing, but if you want to know, you can tell via its polarization. Okay, so this right here is an actual image of the LIGO Hanford and the LIGO Livingston data and what they collected on the September 14th, 2015, about 100 years after Einstein's field equations were actually produced, or general relativity, which is pretty interesting. So this LIGO was actually shut down for 3 years for renovation or construction, and after 3 years, this happened. Literally, they started the LIGO Observatory about 15 minutes later. Many sources say different times, but very short period after, they detected this wave. So as you can see, I'm just going to move a little bit here. As you can see, they are sort of similar, not exactly similar, but one was actually detected 7 milliseconds after the previous one. And as you can see, this, or the maximum amplitude right here, the maximum frequency, is when the black holes just converged and made, as you can see, the most gravitational wave energy, you can say. So when they are orbiting, as I showed you in the animation, they're releasing gravitational waves like every object does. Even we release gravitational waves. But at time of convergence, when the two black holes met, the singularities met and warped space and time together, the most amount of gravitational wave as energy was released, which contributes to the peak amplitude. Okay, hopefully we have actually understood what LIGO is, how it works. So we have kind of sort of completed the first and the second part of my presentation, understanding why LIGO is there and what it's meant to do. So now we're going to come to the fun stuff, the great stuff, gravitational waves, what they really are.